Let us now discuss the Pythagoras concept for similar triangles. Let's see what is the definition of the same and then proceed. In a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Now, have a look at the first theorem. If a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both the sides of the perpendicular are similar to the whole triangle and to each other. How do you prove the same? Let us have a look into it. Given that triangle PQR is a right-angled triangle at Q and perpendicular from Q intersecting PR at S, so we have to prove that triangle PSQ is similar to triangle PQR, triangle QSR is similar to triangle PQR, and triangle PSQ is similar to triangle QSR. Therefore, in triangle PSQ and in triangle PQR, angle P is common. Angle PSQ is equal to angle PQR because each of them are 90 degrees. Therefore, triangle PSQ is similar to triangle PQR by AA similarity criterion. Let's consider this as 1. Similarly, in triangle RSQ and triangle PQR, angle R is common. Angle QSR is equal to angle PQR because each of them is 90 degrees again. Triangle RSQ is similar to triangle PQR by AA similarity criteria. Now let us consider this as 2. So from 1 and 2, we infer that triangle PSQ is similar to triangle PQR and triangle RSQ is similar to triangle PQR. If first triangle is similar to second triangle and second triangle is similar to the third triangle, then first and third triangle are similar. Therefore, triangle PSQ is similar to triangle RSQ, hence proved. Now, let us prove the Pythagoras theorem, which states in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The proof for the same is as follows. Given that triangle ABC is right angled at B, so we have to prove that AC square is equal to AB square plus BC square. So now for construction, we have to draw BD perpendicular to AC. Therefore, since BD perpendicular to AC, now using theorem 1, that is, if a perpendicular is drawn from the vertex of a right angle of a right triangle to the hypotenuse, then the triangles on both the sides of the perpendicular are similar to the whole triangle and to each other. Triangle ADB is similar to triangle ABC. Since sides of similar triangles are in the same ratio, therefore AD by AB is equal to AB by AC. Therefore, AD into AC is equal to AB square. Now, let us consider this as 1. Therefore, triangle BDC is similar to triangle ABC. Since sides of similar triangles are in the same ratio, therefore, CD by BC is equal to BC by AC. Thus, CD into AC is equal to BC square. So, let us consider this as 2. Now, adding 1 and 2, we get AD into AC plus CD into AC is equal to AB square plus BC square. Now, let's take AC common. So, we get AC of AD plus CD is equal to AB square plus BC square. That is, AC into AC is equal to AB square plus BC square. That is, AC square is equal to AB square plus BC square. So, it satisfies the criteria, hence proved. Now, let us take a look into a next theorem, which states that in a triangle, if square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. So, given that a triangle ABC in which AC square is equal to AB square plus BC square, we have to prove that angle B is 90 degrees. So, for construction, let's draw a triangle PQR right angled at Q such that PQ is equal to AB and QR is equal to BC. Now, let us see how to prove the same. In triangle PQR, angle Q is equal to 90 degrees. By Pythagoras theorem, PR square is equal to PQ square plus QR square. Since PQ is equal to AB and QR is equal to BC by construction, PR square is equal to AB square plus BC square. So let us consider this as 1. Also, given that AC square is equal to AB square plus BC square, we can consider this as 2. So, from 1 and 2, PR square is equal to AC square. Therefore, PR is equal to AC. So, let us consider this as 3. Now, in triangle ABC and triangle PQR, AC is equal to PR from 3. So, AB is equal to PQ by construction, BC is equal to QR by construction again. Therefore, triangle ABC is congruent to triangle PQR by SSS congruence rule. Thus, angle B is equal to angle Q because corresponding parts of congruent triangles are always equal. Since angle Q is equal to 90 degree, angle B is equal to 90 degree, hence proved. Now, let us consider a problem. ABC is an equilateral triangle of side 2A. Find each of its altitudes. The solution for the same is as follows. The given figure shows a triangle ABC. Let us draw AD perpendicular to BC. In equilateral triangle ABC, D is the midpoint of BC. Therefore, we can say that BD is equal to DC, which is equal to A. Now, in right angled triangle ADB, AD square is equal to AB square minus BD square, which is equal to 2A to the whole square minus A square, giving you 4A square minus A square, which is equal to 3A square. That is, AD is root 3A square. Therefore, AD is equal to A root 3. As all the altitudes of an equilateral triangle are equal, each of the altitudes of triangle ABC is of length A root 3. Let us summarize all these concepts. First theorem states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and to each other. And Pythagoras theorem states that in a triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. And the final theorem states that in a triangle, if square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle.